Okay, momentum, impulses. Now, let's move into collisions. The total momentum of the system just before collision equals the total momentum just after collision. Okay, conservation of momentum. The total momentum is always conserved for any type of collision. However, the total kinetic energy is generally not conserved in a collision. And we got an idea, from this. We saw this in some of our examples where we did the slide and the guy jumping off of the diving board. When we introduced things that affected the energy, non-conservative forces. So in this case, total momentum is always conserved for any type of collision. However, kinetic energy is generally not conserved in a collision. So let's look at the first category, inelastic collision. An inelastic collision is a collision in which momentum is conserved, but kinetic energy is not. For example, the collision of a rubber ball with a hard surface. Some of the kinetic energy is lost then when the ball is deformed during the contact with the surface. And if you've ever dropped the ball, onto a hard surface, it's got to give some, otherwise it's not going to bounce. A perfectly inelastic collision, okay, second category. When two objects collide and stick together, the collision is a perfectly inelastic collision. For example, the collision of two pieces of putty. They stick together and move with some common velocity after the collision. Two cars hitting and locking together, perfectly inelastic. They move in some direction. Two balls that have Velcro on them stick together and will move in some direction together. So in this case, we rewrite the relationship a little differently to show that the objects stuck together. We have mass 1, velocity 1 initial, plus mass 2, velocity 2 initial, and then we combine the two together, 1 and 2, because they're stuck together, moving at a common velocity final. So we can solve for the common velocity final then just by moving these terms around. And you can see all we did was move m1 plus m2 into the denominator, and boom, we now have a relationship to solve for a perfectly inelastic final velocity. So let's look at an automobile accident. Perfectly inelastic collision. The Cadillac versus the compact car. This isn't going well. Okay, so an 1,800 kilogram luxury sedan stopped at a traffic light is struck from the rear by a compact car with a mass of 900 kilograms. The two cars become entangled as a result of the collision. If the compact car were moving at a velocity of 20 meters per second before the collision, what is the velocity of the entangled mess or mass, whatever you want to call it, after the collision? So here are our givens. The mass of the sedan we'll call M2, the larger, 1,800 kilograms. The mass of the compact we'll call M1, 900 kilograms. And we will call the velocity of the compact V1, 20 meters per second. So we're looking at the velocity of the entangled mass after the collision. So the solution says that before the collision, compact only. Remember I said we're going to divide these up and create boundary problems here. So momentum 1 is equal to mass 1, velocity 1, which gives us a sum of the 900 kilogram car, 20 meters per second, of plus 1.8 times 10 to the 4th kilogram meters per second. So now the momentum final, we know, are the two masses, the two vehicles stuck together times the velocity final. So we're able to solve for velocity final then as P final, M1 plus M2. So 180 times 10 to the 4th kilogram meters per second divided by the sum of the masses. So 2,700 kilograms of the two vehicles stuck together. We're going to divide that into 1.8 times 10 to the fourth kilogram meters per second. And we get a final velocity that the two vehicles move together in unison, stuck together, 6.67 meters per second. Okay, so let's go ahead and stop here. We'll come back and we'll look at the two mud balls that collide together and continue to look at perfectly inelastic collisions.